So I thought I'd start off by talking about the top variation challenges, the top things that our customers at Solido tend to relay back to us as being their biggest problems. And I have a fairly unique perspective into this. I get to work with, our company works with, well over 1,000 individual designers at over 35 companies. And so we get a lot of breadth in terms of what people are concerned about. So at advanced nodes, I mean, everyone says variation's worse. This isn't something new, but it just keeps getting worse. The other thing that's really important is that we've got more corners all the time. So it used to be that we'd have 3 voltages that we'd run corners at. Now people have got 8 or 10 or 12 voltages commonly in production. We've got back bias conditions. It's a continuous variable. You need lots of points in order to cover that. We've got best and worst case extraction conditions, and these are all multiplicative. So instead of people running 30 corners, they're now running 100 corners or 300 corners or something like that. Phenomenal number of corners, and those all need to be covered. At low power, the biggest problem that we have is that our nominal performances drop off really sharply. So performance isn't linear at all. Things start behaving really poorly, even at nominal. And then when you look at statistical performance at low power, what you see is even on simple devices, like I've seen inverters at low nodes where delays, they look like this at our typical supply, and then they start turning into these big long tail distributions. So instead of 3 sigma being here, it's over here somewhere, and you have to measure that really accurately. So we've got this really non-Gaussian behavior at low power, which is really problematic for people that are used to making Gaussian assumptions. And then the last thing here is advanced low power design is really competitive. So you can't just over design anymore. This is what a lot of people did about variation. I think Amit's survey kind of shows that people start getting serious about variation around 55 nanometer. Everyone's kind of doing this. They're not just over designing anymore. You have to add too much over design for this to be a viable method, a viable design method. And time to market's also critical. So now we've got so much more to cover. We can't just over design, but we still have to get our products out fast. We have to get, be first to market or early to market. And so how do you cover all this space with no extra time? So this is where the variation best practices come in play. All things aimed at better coverage and still getting things out within production schedules. So for analog, the things that matter the most are we want to stop using those digital corners. Fast, slow corners don't bound what you're measuring on your analog designs. They weren't ever designed to. It's the wrong thing to vary against. And in fact, it makes things slower because we have to go and cover lots of corners. Instead, we can just use global statistical variation, which is included with every modern process. And then what we can do is pull out at the beginning of our design flow, we can pull out what John was talking about, statistical corners, and Glenn talked about this too, statistical corners, which we can use to iterate quickly against. And these can bound what we're measuring on our analog designs. We can bound gain on your op amp with corners like this. So this is way better than using global process corners. For memory, the biggest thing that I see is there's still a lot of people that aren't doing a good job of verifying even their basic blocks. So their sense amps out to 5.2 sigma and their bit cells out to 6 sigma, their control logic out to 4.1 sigma. People aren't doing this very well. They're still doing Monte Carlo and extrapolating, and there's just no reason for this to be wrong. This is a solved problem for several years. So you really should be using methods that solve this problem. The second thing is, this is actually where things get really hard with memory, I think, is verifying the full statistical design of memory. You can't just throw your whole memory into a SPICE simulator and verify it, so we end up using slices. And then verifying those slices statistically is really hard because what we want is 3 sigma global variation, 4 sigma on our control logic, 5 sigma on our sense amp, 6 sigma on our bit cell all at the same time. And this was an unsolved problem until about a year ago. So this is possible now, and you should be doing it. For standard cell, the hardest thing I think is what to do about low power, because we see our performances drop way off and our distributions become non-Gaussian. So we really need to account for both of those things. We need a lot more precision than we used to have because things don't behave in a very regular way. We also have to verify for replication. So standard cells aren't used with one standard cell on a chip. You're going to have a whole bunch, and they all need to work. It's the problem that John was talking about. A whole bunch of standard cells also, just like memories, that also need to work. And so these are high sigma designs. So standard cells need to be verified to 4 or 5 sigma. They need to be designed for 4 and 5 sigma, and that's really important. And then overall, I think one of the things that bites people in terms of schedule the most is learning about variation problems late in the product development flow, product development cycle. So identifying variation problems early, fixing them early, making sure that you're looking at variation the entire time is really, really important. And then the other thing really is just reducing our uncertainty. So this is why designers over-design. It's not just because they're sloppy. They don't know the right answer. So the chip's got to work. We got to leave some margin. If you can increase the certainty, do more accurate statistical analysis and variation analysis in general, then designers will stop over-designing. And that's really one of the most important things. That's where we see things left on the table more than anywhere else. Amit's survey showed that again this year. So in terms of must-haves to actually accomplish this, the first thing that we need is better basic infrastructure. I work with a lot of customers that don't have a reliable simulation cluster. They don't have a cluster that works, just works day to day, that has licenses available. And it's really hard to do variation analysis if you don't have simulators and clusters that work. We also need managed licenses. I see a lot of cases where companies have enough licenses, but they don't handle bursts, or there's stuff that's checked out and not in use. So managed licenses are really important. The second thing is variation-aware capabilities. One of the things that we do at Solido is we spend probably 80% of our applications engineer time training our users about variation. We're not showing them how tools work or supporting tools. We're teaching them how variation works. And you can do that too within your company. Just train your staff really well, at least at the basics, like really important thing. I think this is something that's generally missing in the industry. Having specialists that you can talk to, whether they're hired on site or external, is really important. So people that you can go and help help designers or help design methodologies for your teams. Developing variation-aware methodologies is really important, and then deploying them. And this isn't something that's best done, I've found, by the CAD team. It's better done by product teams, because the methodologies for variation are product-specific or IP-specific. And so developing really good methodologies that address variation and deploying them group-wide, and group by group ends up being company-wide, is really important. And then targeting over-design again. Really important. Teach people how to do that. Reveal over-design. This is something that people don't even see, right? We don't measure over-design. We don't even know how much there is in a lot of cases. And the last one here, the last must-have is advanced variation tools. So the tools need to be able to implement these methodologies. They should be able to do the thing that you want to do. We want to increase our coverage. We want to have really, really nice accuracy. We want to tools that work reliably. You just push the button, get the answer, and not have to worry about debugging it and things and understanding it. They should really inspire confidence. So if designers think they've got the right answer, they're going to do the right thing, which is shrink margin. And if they don't think they've got the right answer, they're not going to bet their design on that answer. So the tools have to inspire confidence and ultimately eliminate over-design. So the benefits that we see if we do all these things, the first thing is that we're going to deliver reliably ahead of schedule. We're not going to have variation problems that are going to lead to respins, which lead to months of delay. Time to market's really important, so decreasing that schedule risk is really important. And then the other thing is we're going to have 10 to 60% less over-design. So we heard a case here today where over-design was reduced by about 30% on something that was already tuned. That's pretty typical. That's what you see if you're doing variation-aware design right. So power, performance, and area, more competitive products. That's what it's all about.